Okay, hi everybody. In this video, we're going to take a look at what's called the continuity correction that we can apply when we use a continuous distribution, normal distribution in this case, to approximate a discrete distribution. So the discrete distribution we're going to consider is binomial distribution. So let's imagine here that we are flipping a coin 10 times and it's a fair coin, and we want to calculate our success here. X is going to be the number of times we get a head. So if we wanted to approximate what's the probability out of 10 flips that we get 3 or 4 heads, then we could use, say, R to calculate this probability precisely. And what that code would look like in R, we would use, for example, we can use D binom. So remember, D binom calculates the probability of getting exactly 4 successes. And so what is going on here is this first one is telling us what's the probability of getting exactly 4 successes. This is telling us what's the probability of getting exactly 3 successes. And now when I add those two together, right, that's going to give me the probability of getting at least 3, but no more than 4 successes. So there's only 2 possibilities here since we can't get a fractional amount of heads. That would be either 3 or 4. And so from what we've discussed already with binomial distributions in R, we would see that that would be 0.322. So here's the output from R. And now let's think about another way that we could approximate this using central limit theorem approximation for this binomial distribution. So what's going on in this figure here, in the background with the bars, we have the binomial distribution. So remember, x, the number of heads that we get, is discrete. So we can only count them being 0, 1, 2, 3, 4, etc. And we can't get a decimal value for the number of heads. But we can approximate this binomial distribution with the continuous random variable using the central limit theorem, using a normal distribution. So this random variable x that we have here, it has a mean, which is equal to n times p, which would be the 0.5 times the 10. So we would expect, on average, to get 5 heads out of 10 if the coin is fair. And we can calculate the standard deviation of x using the shortcut that the variance is going to equal n times p times q. And so if we calculate that, that actually winds up being 1.581. So here we're using n is 10, p is 0.5, and q, the probability of a failure, is also 0.5. So that's what this distribution, this normal distribution that is drawn on top of the binomial distribution is given by. So we can approximate x with a normal distribution with a mean of 5 and a standard deviation of 1.581, for example. And then I could use R to come up with an estimate for the probability that x is between 3 and 4, which we've got here. So now we would use the p-norm function. So that's going to calculate, the first piece is going to calculate the area to the left of 4. And then we're going to subtract from that the area to the left of 3, which is what the second p-norm is doing. And altogether, that's going to give us the area between 3 and 4 underneath the normal distribution. Okay, and we saw in the previous slide that we got something like 0.32, and here we're getting something much, much smaller, like 0.16. And so why are we getting this underestimate? Well, if we look at the graph, let's kind of mark the value where 3 is. So 3 would be about here, 4 is here. So when I calculate the area underneath the normal distribution, essentially what we're getting is all of this stuff over here. And so we're missing some stuff over here, and we're missing some stuff over here. and that's causing the problem. So we're missing a lot of area and we're getting an underestimate. Take a look, generally speaking, what we can do for the continuity correction is go a little bit to the left of the lower value A, half a unit say, and we can go a little bit to the right of the upper limit, which is B. And this is gonna give us a little additional area that's gonna balance out those missing portions. So using the same sort of normal distribution approximation here, notice I changed the 4 to a 4.5. I changed the 3 to a 2.5. So I went half a unit further in each direction, and we got something that is much, much closer to what we would have expected to get, since we know how to calculate this exactly using the binomial distribution. So we can compare all of these estimates. This is the estimate we get with the continuity correction. This was the exact value, not perfect, but much better than the approximation we got without the continuity correction. And so the issue here is we're using a continuous normal distribution to approximate a discrete binomial distribution. And so going these half a units further to the left or to the right are adding up kind of the full bars that we saw over 3 and over 4 in the discrete distribution. And we're going to kind of include those little slivers of area that we left out when we started at 3 exactly and at 4 exactly. We weren't getting the full area of those two rectangles.